We're going to look at some examples of predicting chemical reactions. And these come in a variety of forms. As you see, they can occur. We can predict we can predict these reactions, whether they're single replacement, double replacement, synthesis, decomposition, combustion. And so a good skill in chemistry is knowing what products to expect. If you know what you're putting together, if you know what you're mixing, uh, what's going to be the result. If you know the compounds that you're starting with, you can make a pretty good prediction of the products by going through some steps and thinking about oxidation states. So, oxidation states or numbers uh, can be looked up, but you need to think about uh, what those charges will be uh, on the different elements involved. So, looking at this single replacement reaction, we have zinc and sulfur mixing with diatomic oxygen. And so we need to know, first of all, so we're going to be asking how those uh, how those elements recombine in the products and in what amounts, in what ratios will they recombine. So let's look up the oxidation numbers for our three elements here. We want to know the oxidation numbers for zinc, sulfur, and oxygen. And you can look those up, and they are just what they really mean is if you were to break these into ions, what would the charges be if you separated these elements out? And so zinc happens to be +2, oxygen happens to be -2, and sulfur happens to be -2. We know in a single replacement that uh, part of a combined compound is going to split and recombine with a single that comes in. So we're either expecting the zinc or the sulfur to somehow recombine with that oxygen, and then we'll have a different, it's like swapping a partner on a dance floor. Somebody will step out and the other two will form a new couple. So, looking to our oxidation states, we see that oxygen uh, is a -2. We want to find the opposite. We want to find the opposite charge in this other compound, and so look to whatever the positive charge is over here. And so in this case, the positive is zinc with a +2. So we know that zinc has a +2. So that tells us that those two opposite oxidation states are going to be drawn together and form a new compound. So we know that our new product is going to be some form of zinc and oxygen. But how much zinc and how much oxygen is the question. To figure that out, you have to combine these two oxidation numbers in the ratios that they exist to each other. So since there's a +2, and think of that as combining with a -2, since they're the same number but opposite, think of them as canceling each other out, and the most simplified ratio is simply 1:1. So that tells us that zinc and oxygen combine together in a 1:1 ratio. They don't have any subscripts with them. So zinc oxide will be one compound, and then whatever's left over. We see that sulfur gets kicked off and becomes a single element by itself. That is the prediction part of that reaction. And then you would have to go on, once you have those reactants and products figured out, you would have to go on and do the balancing, which is usually pretty straightforward, and you should have had some practice with this already. So really quick, I see that there are 2 oxygen, so we're going to need a 2 coefficient. That gives us 2 zincs, so a 2 would have to go here as well, and then 2 sulfurs and 2 sulfurs. A double replacement reaction will work much the same way, except we'll have a little bit different mechanics going on in terms of the partners swapping places. So in double replacements, we know that there are 2 compounds that are each going to be split and switch with each other. So first let's kind of break down what parts we have. In our first compound, we have the part which is a calcium, and then we have a hydroxide group. And that you can see is kind of its own thing. It stays together as a whole. So you'll see that the hydroxide group stays together as a whole during this reaction. So we'll think of it as a single item. And then in our other compound, we have hydrogen and chlorine. Okay. Again, let's look up the oxidation states, and you'll probably eventually start to memorize these, but they can be looked up. Calcium oxidation state is +2. Hydroxide is -1. Hydrogens are +1 by themselves, and chlorines are -1. So those are the oxidation states, or oxidation numbers for those different parts. Okay, so here's where the swap is going to happen. So we know that calcium and hydroxide are going to split. Hydrogen and chlorine are going to split. How do we know who ends up with whom? Look to the positives and negatives in those groups. Calcium, since calcium is a positive number, it's going to be looking for another negative partner. So it's already with hydroxide, but it could also match with chlorine if they split. So in our products, we have calcium and chlorine together. Now, calcium comes in as a +2. Chlorine comes in as a -1. Think of those numbers as kind of crossing and forming a ratio to the other one is kind of how I think of it in my head. So that this is what I mean. So because calcium is +2, a 2 goes down, and you need 2 chlorines to match with that calcium. So in other words, those numbers kind of cross. The -1 tells you that there's a single calcium. The +2 tells you that there are 2 chlorines. So I hope you can see how I did that, why I took that number, and it's just kind of a mechanical thing to know that switches over to the other partner, and it means that your compound there is going to be CaCl2. Okay, let's do the same thing for our other part of this reaction. So we also have hydroxide looking for a partner. And again, hydroxide is negative. It's looking for a positive partner. This is a great match between hydroxide and a lone hydrogen atom. So you'll have hydroxide and hydrogen coming together. Hydroxide brings a -1. Hydrogen brings a +1. This is easy. When the numbers are the same, it's a 1-to-1 ratio. but you could still kind of think of those numbers as crossing and becoming the subscripts for each other. So what that ultimately gives us is HOH, which we can rewrite as two H's, H2O. So those are our products of this double replacement reaction. So in other words, the calcium chloride and water are the products of that reaction.